Hello everyone, it's Diana here. We will continue with another category of energy storage system, which is thermal energy storage. We will learn about three different ways of storing and releasing the thermal energy across this topic. So let's find out. So in this topic, I will try to cover within 15 to 30 minutes in terms of the terminology of thermal energy storage and the general methods of operation, and of course three different methods of storing and releasing the thermal energy. And of course I provide you some references and additional terminology for you. I refer to a published review article in 2021 about the general meaning of thermal energy storage, or we can short form it as TESS. So TESS stores the energy through heating or melting the materials in the form of sensible heat, latent heat, or thermochemical reaction. Also, TESS is the most suitable technology to be integrated with renewable energy into grid system and has a very wide application. So among the feasible applications using TESS include integrating with solar energy, conserving building energy in terms of managing the electronic or electric equipment, and waste heat recovery. In general, TESS requires storage media such as the solid, liquid, and gas, and the equipment which injects and extracts in the media such as heat transfer fluid or heat exchanger. However, it depends on which type of TESS techniques we apply for. There are three methods to charge and discharge the energy using the thermal operation. Number one is the sensible heating, and then number two, latent heating, and next one will be thermochemical heating. So for the sensible heating, it depends on the heat transfer into a medium through the increase in the temperature of the medium, while for the latent heating, the stored and the released energy will be based on the phase change or the phase transition of the latent heat, whether it is from a solid to a liquid or from a liquid to a gas, or vice versa. The last but not least would be the occurrence of the thermochemical heating can be understood by the reversible thermochemical reactions. We will start with the sensible heating system. So, sensible heating stores the energy through direct heating on a medium, whether it is a solid or a liquid, which causes a change in the temperature but without the phase change. This is a very simple method to store and release the thermal energy, and it's a very important aspect to acquire an optimum performance of this system will be depending on the material's specific heat capacity, its density, the material's thermal conductivity, the operating temperature, and of course some cases which also look at how compatible to mix between different materials. The normal medium type, which is water, has the boiling point of 100 degrees Celsius. Of course, the water has high specific heat capacity, and of course it is an abundant resource which can be quite cheap to use. There are some other media which we can use to provide this type of heating, which usually has higher boiling point, more than 100 degrees Celsius, such as we can use heat transfer oil, liquid sodium, concrete, and also molten nitrates. Let's move to the basic components required for the sensible heating system. Of course, the first one we need is a storage where a medium can be stored, and then we also need the medium, whether it is in a liquid form or it is in the solid form. We also need a network such as pipes or conduits, which are used to transport the heat from and into a medium. Usually another type of medium will be used to provide heat. Then we need a temperature regulator or a temperature control system to operate and regulate the temperatures in different conditions. So the energy capacity that is stored in a medium through this system can be understood depends on the operating temperature range, The TH considers the highest operating temperature, while the TL is the lowest operating temperature. And another consideration is on the heat capacity of the storage media, which is the CP. So the sensible heating system can be greatly influenced based on the heat capacity per medium or per material. Also note that the thermal conductivity of each material or the medium can also determine the conductive rate of the heat to be transferred from and to another medium. Now we'll look at the system performance. Of course, we will start with the ideal features. The ideal features can be based on the type of the medium used for the system. For liquid type, water can be an optimal material for low temperature range, but it also offers high specific heat capacity and quite cheap to use. The application can be in diverse scale from small to large, and then if you want to use solid type, metals and rods are better to deal for the application which cannot tolerate frozen and melting states, which these can overcome the solution of the limitation of the liquid media. Now we move to the system advantage. The first one, of course, it has low to high temperature range, high specific heat capacity, and then low material costs. And then number 4, environmentally friendly, which is non-toxic materials we are going to use. And yes, it is suitable for large-scale application. Of course, the system has challenges, which some materials has low energy storage density. The materials can be packed or installed according to the system design, which these, of course, if we want to have higher performance, definitely we need to have large volumes to ensure that it can produce more energy. High capacity costs for the system installation, and some materials can cause defects as well. And different in the materials of pipe system when transporting the heat transfer fluid to the solid medium can reduce the heat transfer performance. Among the known application of sensible heating system is soil and ground source heat storage, where the storage is commonly built underground and the heat pump will be connected to the storage medium. So some new application, of course, it use renewable energy systems to charge the pump hydro system, and then the heat pump will then charge the storage medium during high excess power. So whenever we want to use the stored energy, the energy will be discharged from the medium and will be circulated throughout the heat pump before the heating is circulated to provide building energy. Also, another sensible heating application can also be seen from a storage plant, usually commonly integrated with solar PV systems, where it can be built as a standalone unit, or it can be part of the power grid. Next, we will move to latent heat storage system. So latent heating use a reverse fundamental to the sensible heating, where the energy will be stored and released during the phase change process with a very nominal or very less temperature change. However, the system performance will definitely depend on the density of the medium used, the specific heat capacity, the thermal conductivity, and the operating temperature, and also the compatible between the medium, of course. We can refer to the figure on the left to look at the basic components needed for this system. The main one should be, of course, the phase change materials, or we short form it in as PCM, these medium, and also the containers as the storage. Then we need the heat exchanger, in which these include the heat transfer fluid, HTF, the pipes or the conduits to transfer the HTF, and then we also need the power system or a control system which to assist in terms of charging and discharging the system. There will be three categories of the phase change materials, or PCM. We have the organic types such as paraffin, and the non-paraffin type, which is fatty acids or polymers. These types of material require the change phase process above 0 degrees Celsius, and they can freeze and melt repeatedly without phase separation. Then we also have the inorganic materials, which include salt hydrate base and also metallic base. The salt hydrate types requires the hydration process during the phase change from solid to liquid, where the hydrate crystal will decompose into lower hydrates and also water. So some salts can also incorporate water of crystallization during the freezing process, which usually takes place above 0 degrees Celsius. For the metallic type, of course, this type of PCM can be said to be able to enhance the thermal conductivity and to expedite the speed of the phase change. Another PCM category is the eutectic type, where it is composed by the mixture of two or more components, whether it can be between organic and organic type, or inorganic type, or organic and inorganic type. So these material will be able to avoid phase separation after the crystal is established because of multiple components crystallized together. The equation of calculating the stored energy, which is Q, for this system is almost similar to sensible heating, but the difference can be noticed from the phase change enthalpy of the material, which is H, which is required to complete the equation. And also we need to have the solidus and liquidus temperatures of the material. So the TL here is the PCM temperature in solid, and also the TS is the PCM temperature in the liquid. So some examples of thermophysical data of some PCMs are shown. Note that from the table it shows the heat fusion. The heat of fusion in the unit of kJ per kg. And it can be a bit confusing which one is the enthalpy of the PC and why it is not presented in heat of fusion instead. So there is actually like no difference between the heat of fusion and the enthalpy, as the latent heat of fusion of a PCM is actually equivalent to the enthalpy change during the melting process. Next, we will learn about the system performance in overall. Definitely I will not go through all, but just highlight you the important ones. For the ideal features of the latent heat, I will go for number 1, 2, and 4. So number 1, the phase transition temperature should match the operating temperature range of the system. Number 2, the phase transition specific heat should be large enough to achieve high thermal conductivity rate. And number 4, the volume change should be minimal to ensure the feasibility of the container and also the heat exchange structure. In terms of the system advantage, I will go for number 2 and 10. So number 2 will be it contains small range of temperature change, and number 10, it has high volumetric energy density. For the system challenges, I'll go for number 3 and 7, which some materials are not compatible with plastic containers, and of course some materials is easily to supercool. Now we will look at the system performance comparing different types of PCM categories. I will not go into details, but only highlight you the main features. We will start with the organic type. The main advantage of this material is it has no overcooling or supercooling effect, which easily to happen to the salt hydrate base. But of course, these type of materials are flammable. It's not suitable with plastic containers. It cause low energy storage density and can be slightly corrosive if we choose to use fatty acid. For the organic type, the main advantage of these materials, they have good thermal conductivity. They are non-toxic and non-corrosive type, and they have high volumetric energy density and high thermal conductivity if we use metallic type. In contrary, the system can easily supercool, where during this state, the temperature of the melted material is cooled below 0 degrees Celsius, but without change its phase to solid, or it won't crystallize. That's the problem. For the eutectic type, we can say that it has both combined performance of organic and inorganic types. I mean, of course, depends on which combination it will be. And of course, making it into eutectic, the material can be able to reduce or minimize their disadvantage and are more efficient in terms of energy storage density. There are some recent advanced findings based on this system. Number one, some studies try to develop a higher temperature range of PCM storage system between 230 to 330 degrees Celsius, where it can be suitable or be applicable for large-scale use. Also, there's an attempt to integrate fins inside an enclosed PCM tank or maybe pipes, which can be able to reduce the melting time while it also increase the thermal conductivity of the material. Now we'll go to the application of the system. So latent heating system is quite common for small to medium scale use, such as can be integrated with building energy system to provide indoor thermal comfort and also HVAC. For large application, a PCM test can be quite suitably designed with industrial plants, where the PCM test can be able to store the waste heat or any combustion heat came from the high temperature exhaust gas and can be able to release the thermal heat energy whenever it is needed. There's another novel application. It's reported to have the integration of metallic PCM with the electric vehicles, the EV, where of course there is an attempt to store the heat which is discharged from the battery. So means that the PCM acts like a thermal regulator to the battery, which of course to make sure that the batteries used to drive the EV can be more efficient. Now let's continue with the thermochemical heat storage system. So now we will start with the operating principle of thermochemical heat storage system. So this system is easily understood by storing and releasing thermal heat or thermal energy in the form of reversible chemical reaction. So the reaction can be due to normal chemical reaction or photochemical reactions or hydrate reaction. This system has high potential as it can store and produce very high energy density, and it is feasible to be integrated with renewable resources. The problem with this storage type is it causes instability in the chemical compounds, which this one will be obtained during charging and discharging process. Okay, then we'll start to learn on how this system will work during the charging period. Just note that A will be used as a material to store and release the heat through the thermochemical process. So we can refer to the figure on the right side. It's very easy to understand. During the charging period, first we have to apply heat, which is Q, to A, which causes A to separate into two parts, which is B and also C. So both parts here will be separated and stored until the discharge process is required. So usually, definitely, we need to have containers to keep both chemical compounds. Then during the discharging process, the B and C will be mixed, and it will become will back to material A, plus the Q, the heat, will be released. Of course, there will be a little thermal loss should be expected during this process because of the unstable chemical reaction between B and C. To understand on how Q, or the thermal heat or the thermal energy, can be stored through this chemical reaction, the components that govern the equation will be the mass of the reactant, the material specific heat capacity, and also the enthalpy change per unit mass of the reactant. Here just show some examples of the chemical reactions to produce the thermochemical heat storage system. Now let's move to the system performance in overall. We'll start with the ideal features. Of course, the ideal features of the system include it has the capacity to store and release a long-term energy to the power grid system. And there will be redundant electric energy which can be potentially converted into heat energy because the absorber of the system contains these thermochemical materials. Among the advantage of the system, it has high energy density, low thermal loss, and there are many suitable catalysts to produce the chemical reactions. Of course, the system has some challenges. It can cause corrosion and then a little shaky during the material development, which these can lead to poor heat transfer performance. Also, the configuration of the heat exchanger and the reactor will play significant roles to maintain and increase the system performance, which these can be a little troublesome to produce the system. I hope that we can still remember that we have learned about the adiabatic compressed air energy storage, adiabatic AES, in the previous slide on mechanically operated technologies. So among the new findings on thermochemical heat storage system is by utilizing thermochemical process as a heat recovery for the adiabatic AES, where this type of storage, it assists in terms of keeping and releasing the heat or the temperature to the air during the pressurization and expansion states. This integration, of course, it eliminates the use of fossil fuels, which is a great advantage towards decarbonizing the energy production of the whole CAS system. The common application of thermochemical storage is almost similar to the previous sensible and latent heating methods. For building energy storage, it can be combined with HVAC, especially for heating. And then another application is reported to couple the thermochemical heat storage system with solar system as an effective way to store and capture the energy from the sun. And of course, the research is driven based on the which catalyst is used to produce the chemical reactions. We are approaching to the end of the lecture, so there are some references here, very good to go. Whenever you are free, definitely you can always check on them to gain better understanding on the operation of thermally operated energy storage technologies. Here as well, I really encourage you to check on these published materials. And of course, some website links here are very useful resources. Some terms are also provided here. And yes, thank you very much for your attention. We'll continue with the next topic on the next slide. Okay, bye-bye.